All right, in this video, I'm going to talk a little bit about how energy transfers due to a temperature difference. So here I have two blocks. One is at a high temperature, and the other block is at a low temperature. And based on your experience in the world, you know that there is going to be a situation where the low temperature block becomes warmer and the high temperature block becomes cooler because they are in contact with each other. And so the idea here is, how does that actually happen? So if we think about the block in terms of the atoms that are inside of it, the high temperature block has atoms that are jiggling really, really fast. They have a lot of kinetic energy. Some of that kinetic energy is associated with random motion, and it's what we've called thermal energy. And so the thermal energy per atom is very high in a high temperature block. And so those atoms are moving around very quickly. Whereas in the low temperature block, there's not as much kinetic energy of the atoms. They're not jiggling quite as fast. They have lower thermal energy per atom on average. And so at the interface here, what you have is a situation where these fast-moving atoms in the high temperature block run into the slow-moving atoms in the low temperature block and transfer their kinetic energy across the boundary. Then that allows atoms in the near the interface colliding. They collide with the other atoms all along the way here, transferring kinetic energy throughout the rest of this block. And so as a result, what happens is a lot of the thermal energy that was in the high temperature block moves across the boundary through these microscopic collisions with other atoms, so that the low temperature block gains thermal energy. Now, this transfer of energy across this boundary we refer to often as heat. And that's a really loaded word. It has a lot of baggage associated with it because we use it colloquially a lot. So I don't want to use that word. What I want to use instead is this idea of an energy transfer due to a temperature difference. We'll give that a symbol, Q, and we'll distinguish it from the other types of energy transfers that we have in the sense that it is done microscopically. So we'll actually refer to it as microscopic work because what it actually is the impact of these fast-moving atoms in the high temperature block running into the slower-moving atoms in the low temperature block. So this is to distinguish it from the other kind of work that you are have already worked with, which is the force times the displacement, which we would call macroscopic work. So both of these things, the macroscopic work, which is actually pushing objects around and so forth, and the microscopic work, which is the collisions between atoms at a boundary, can transfer energy in a system. And so we can try to understand a little bit about what this Q is and what it looks like when you have different types of systems. What we'll find is, in fact, that Q can take on positive and negative values depending on the system you're looking at. So for a moment, let's consider the high temperature block. And we know that there is some thermal energy that is going across this boundary. It's going out of the system. And so if we're going to connect this to the energy principle, we know that the thermal energy of this high temperature block is going down. There's going to be less jiggling of the atoms as a result of this energy being transferred out of the system. And if that's the case, we know from the energy principle that this thermal energy is going to be associated with heat exchange to the surroundings. And so if the change in thermal energy is negative, Q is negative for that situation. You're taking thermal energy out of the system. On the other hand, if we're looking at the low temperature block as our system, we know that the thermal energy change there is going to be positive. The atoms are going to start jiggling more. The temperature of that system is going to go up. And so because this change in thermal energy, again, is associated with a heat exchange or with microscopic work, the Q here is going to be positive. So a situation where you have thermal energy leaving a system corresponds to a negative Q, or a negative micro work. A situation where you have thermal energy coming into a system is where you have a positive Q, or positive microscopic work. So getting those signs right is really, really challenging. But keep in mind this sort of picture of, is it a high temperature system that has thermal energy leaving it, or is it a low temperature system that has thermal energy coming into it?